Hello, my name is Jared. I'm a PhD student at the University of Washington, and today I'll be talking about our work in understanding human perspectives and scalably detecting disability parking. Accessible parking is crucial for people with disabilities. Since the Americans with Disabilities Act was passed in the US in 1990, 4 to 8% of all public parking is mandated to be dedicated for disability parking. Despite this, within the Act, there are no compliance verification measures embedded. So what this means is that despite there being a long list of what constitutes a proper disability parking space in terms of like width and location, there has been no large-scale study of disability parking nor audit of disability parking in the United States. And there's little work understanding how people actually use disability parking and if it's good or bad in its current state. To that end, today I'll be talking about our work, first with an interview study with several people with disabilities on how they use disability parking. Then I'll talk about a computer vision pipeline that we developed to scalably detect and audit disability parking. And then lastly, I'll talk about some potential new applications for our work. So starting with the interview study, we recruited 11 participants with disabilities who are eligible for disability parking. This meant that either they themselves had a permanent or temporary disability, or they were the primary driver for somebody who did have a disability. We conducted an interview split into 3 parts, firstly asking how disability parking fits into their transportation decisions and lifestyle. Secondly, what do participants like and dislike about disability parking as it stands now? And then lastly, we discussed a little bit about technology tools and how they see technology tools potentially working in this space. Coming to the results, firstly, we found that disability parking needs varied highly between individuals. Most commonly was simply just having enough space to get in and out of their car. For example, if the car can fit in and I can get in and out, that's all I look for. This need often dominated other aspects like distance from the entrance. As long as I can use my equipment, I don't mind going further, but other times without sidewalks and curb cuts, there have been times when I couldn't park anywhere. Other participants called out the design of the spaces themselves. Most access aisles are on the right side, why not the left? Doesn't make any sense for me, except for if somebody's in a manual chair. These highly personalized needs meant that users often had to adapt to situations or create their own accessible parking. There's been quite a few times when I've had to either create my own space or illegally park in a bank that was closed. However, creating your own parking is obviously not ideal. I'll park out over the white line, and then you come back and you can see people who got really annoyed, and it's like, I'm sorry, I can't help it. This meant that users often had to evaluate how important the trip actually was for them to take. I do math in my head about how badly do I need to go to the store today. Coming to technology tools, many users felt that tools that help them understand the state of the world or understand the state of parking, where they're going, would be the most helpful. I don't necessarily know whether there's a flight of stairs or the accessible ramp is that way. Just having that extra information, it can't not help. If you could say, all of these are full, the next closest ADA spot is here, that would be pretty cool. However, there are, of course, privacy and trust concerns with this approach. I don't want somebody else's computer program getting me the information that I want when I can just do it myself. Using the results from this formative study that we did, we then set out to develop a computer vision pipeline that could scalably detect and audit disability parking. Well, to do so, we first needed a data set of disability parking, of which none existed at the time. So we had to make one. We downloaded images from 3 different cities across the US, Seattle, Washington, DC, and Spring Hill, Tennessee, totaling 5,125 images. We then labeled all of those images for any disability parking, and we split it into both access aisles and type of disability parking. For example, in the top, we have a parking space with 2 aisles, and in the bottom, we have a parking space with 1 aisle. In total, we had 11,762 labeled parking objects across several different classes. I will note that there is a significant dataset imbalance, which does slightly impact results, as I'll discuss later. I'd like to take this moment and say that the dataset is released and open sourced, and you can download it now on Hugging Face or at GitHub. Now that we have a dataset, we can train some models. So we'll start out with object detection. What we did is we used a state-of-the-art object detection model, CodeEditor. We fine-tuned it using our dataset to draw bounding boxes around any potential disability parking spaces from aerial imagery, like so. Then, using the output from our object detection model, we trained an oriented bounding box model to get a better understanding of the actual geometry of the spaces. So we used YOLO V11X in the oriented bounding box model, and it created oriented bounding boxes as such. So we can get bounding boxes that are aligned with the axis of the parking space itself. So this lets us do some calculate some interesting statistics about the parking spaces themselves, in particular width. So we're able to calculate the width by just simply measuring the width of the oriented bounding boxes that were detected. Coming to object detection performance, we first evaluated our models both on a test subset of the dataset and 4 manually labeled 1 kilometer square regions in our test regions. We find relatively good performance across the 3 machine learning statistics, F1, recall, and precision, around the mid-80s to 90s. But to get a more generalized understanding of the performance, we also tested it on 3 manually labeled 1 kilometer square regions outside of our train set. We find that while performance is slightly worse for F1 and precision, for recall, it's actually comparable. And we'd like to note that we actually specifically trained the models to have high recall, as we feel that in this context, correcting a false positive is much easier than finding a false negative. So to see the results being comparable to within the trained cities is very encouraging. Taking a look at where the models performed worse, we often see false positives in cases where there's occlusion or blurry images, or maybe there's some logo that kind of looks like a disability parking logo from the aerial imagery, but it's not actually. As for the spaces that it missed, or the false negatives, this often came down to, again, occlusion or blurry imagery. For accuracy in determining the width of the parking spaces, we found that on average, the model overestimated the width by 5.4%, with a standard deviation of 17.5%. But to get a frame of reference for how good this actually is, we had 2 humans label the same subset of our data set and compared their width to each other. And we actually found that while they did perform a little bit better with an average overestimation of 1.8% and a standard deviation of 12.1, that's actually not that much better than the machine learning that the ML pipeline did, and we see the same pattern of a high standard deviation. We can also split the results by class. So we see the results for 1-aisle parking, 2-aisle parking, and no-aisle parking. And we observe that the model and the humans perform the best on 2-aisle parking, perhaps because they are the widest, and they perform the worst on the no-aisle parking. And particularly in this case, the no-aisle parking is one of the least represented in our data set, so that may explain the high standard deviation from the model. So where does this all bring us? We ran our pipeline on the entirety of Seattle, which you can see here. Every dot is a potential disability parking space, characterized both in terms of location and its geometry. Using this, we can really start to dig into into the scalable auditing aspect of our work. For example, looking at where there are clusters of disability parking, or maybe more importantly, where there's no clusters of disability parking. This finally brings us to our final section, where I'd like to talk about some potential uses for our findings and results. We think of uses on 2 levels. First, a policy level, where local governments can inspect disability parking and observe where it aligns with regulation or where it doesn't on a macro scale. But then there's also an individual level, where individuals can find and filter for disability parking that specifically suits their needs, responding to the needs that our participants described in the interview study. Today, I've talked about our work to understand disability parking and scalably audit it. In the end, we contribute formative findings on how people with disabilities navigate disability parking, an open source dataset of almost 12,000 labeled disability parking objects, and a CV tool that locates, classifies, and characterizes disability parking from widely available aerial imagery. Thank you, and I'll take this time to say that I am looking for internships in the summer. I have a background in machine learning, and I'm interested in applied ML and human AI. Thank you.